So last week we got started on digital information. So pretty much how data is being stored in a computer. We talked about different kinds of data that is stored and how they are stored. We didn't get too far into digital information. What we did cover, however, was how numbers were stored, and we covered how text is stored. Now, when it comes to this right here, for this PowerPoint, we're going to be talking a little bit more about images, how images are being stored in a computer. Because when it comes to images, sometimes it's very difficult to understand how a picture can be saved using numbers, specifically binary numbers. Remember, everything in a computer is stored as a binary number or a set of binary numbers. So sometimes it's a little bit difficult to understand how that translation occurs. So today we're going to be talking about images, and later, if we have time, we will be talking about data compression, because with data, you are using storage. And if you are using a lot of storage, sometimes it's beneficial for you to be able to minimize the amount of storage that you use. That way you can maximize the amount of things that you can hold in a computer. So those are the target topics for today. But if it doesn't work out, fine. Next week. I introduced how data can be processed. So there's 4 different things that I talked about and didn't really have time to expand on because we were running out of time. But first of all, there's cleaning. So cleaning is removing corrupt data, removing or repairing incomplete data, and verifying ranges or dates. So pretty much you are making sure the data you have is a good representation of what you are trying to study. Sometimes you'll find that some of the data is incorrect or it just doesn't make sense. Maybe someone added an extra 1 in when they were doing when they were transferring the data over, or someone accidentally deleted a sample or like a cell from your data. In that case, you want to clean up your data so that it, while truly representing what the data is supposed to represent, you could also clean up and fix whatever is incorrect. So really the purpose of cleaning is to fix data without altering the representation. So if you are cleaning the data, but you're completely changing the meaning of it, that's not cleaning. You're just messing with the data at that point. So cleaning is supposed to help you without you changing the data itself or changing the meaning of the data. Then we have filtering. So filtering is identifying and extracting different subsets to help people make meaning of the data. So filtering is almost in a way like the second thing that we're going to talk about, which is classifying, but it's a tool. Filtering is a tool for finding information, and it helps you recognize patterns. So filtering, and so it's exactly what it sounds like when you are filtering your emails. You're trying to bring down all, let's say you have 1,000 emails, but you're trying to look for an email sent by me. Then you could filter all emails sent by me, because the other emails have no meaning to you because those are not sent by me. So filtering will narrow down your search. So this is another way that data can be processed. Then we also have classifying. So classifying data is for it's clustering data. So finding similarities in your data set so that you could gather more information or gain insight from it. So clustering, actually let me use a different color so it's clear. So this is clustering data or data clustering, clustering data to gain insights. So the act of clustering would be the act of classifying. So this group of data is like all males, like data is from all male. And then this group over here is data for all females. Then you would be able to compare and contrast to see if there is more information or any implications that you can gather from this data. And finally, pattern recognition. So identifying patterns in data that people are unable to recognize or cannot process enough data to see the pattern. So this kind of goes hand in hand with like the other things that we talked about: cleaning, filtering, classifying, and patterns. In fact, pattern recognition is probably one of the more, in my opinion, interesting fields of computer science. Sometimes as humans, where we have limitations to processing data because we are human, we don't compute as fast as computers do, we could filter data, classify data in order to help us find these patterns. And in my opinion, like I said, completely my opinion, pattern recognition is a very important aspect of computer science and data science. I'm not being biased at all here. So these are the 4 major ones that you guys should know about how data can be processed. Another thing I actually did not have time, so I guess this is new material now. We didn't have time to talk about it last week. 2 sets of vocabulary words, big data and metadata. You guys probably have heard these 2 words thrown around, but maybe you guys don't know exactly what it means. These are important vocab words that you 100% need to know for the AP Computer Science Principles test. So big data, surprisingly, means large sets of data. Shocker, right? So big data does not mean large numbers, but large amounts of data. So big data doesn't mean you have a huge number stored as a value for data, but just means you have a lot of data stored. So much that it cannot fit into the available memory of our computers or servers. So the data that you guys work with every day, like your Google Sheets or like Google Doc file or a PDF that you downloaded or just something that you saved on your computer, like a computer game that you have, that's not big data. It's not large enough to be considered big data. Big data is normally associated with large corporations, especially when it comes to like tech companies. But big data could even just be like from like a database. So if you go to a hospital, they probably have files for every single patient that they have. That's probably, depending on the size of the hospital, is going to be considered big data because they have so much information. When you think about, I mean, actually, and what's relevant today is what kind of information corporations have on us. So a lot of people, when it comes to data privacy, which we will be talking about probably next week, controversial topic, how much is too much that, or how much data is too much data that companies have on us. The big thing people are saying now is, oh, Google knows everything about you because everyone uses Google, or let's say like Android, like those kinds of companies. They're always dealing with big data because they have so much data. So that's what big data is. Hopefully that clarifies things. So big data doesn't necessarily mean large data values. It just means a large amount of data. The other thing is metadata. Metadata is data that describes data. Very meta. So metadata usually helps, what am I trying to say? Usually helps other find data. I think I meant, yikes. I think I meant usually helps find other data and use it more effectively. I think that's what I meant. So an example of metadata. So let's say you have, you make a document, like you make a Google Sheets document. Normally next to the Google Sheets, or actually Google Doc, I guess you guys use Google Doc. Next to the Google Doc, it tells you exactly what day and what time it was created, and it could also tell you when it was last edited. That is metadata. you did not necessarily create that Google Doc with the intention of storing when you created it and when you edit it. But that data that describes the data that you have just created is an example of metadata. There's other kinds of metadata as well. So let's say you create um, let's say you're using Photoshop and you are creating a picture, you're creating an image of like length and width. That length and width, that is also an example of metadata. It's not a direct consequence. I mean, it is created by consequence of what you have, the data that you have actually made, which is the image. So metadata is not exactly the data itself, it is describing the data. That is what metadata is. And we are going to get into examples of metadata shortly. So if you're still confused about metadata, hopefully the examples that we do will clarify things. But these are two big vocabulary words that you should know for the principles exam. Big data is more something that is relevant in today's society when it, sorry, let me rephrase that. It's more relevant for the AP Computer Science Principles test as a computational innovation kind of question and potentially like a current events kind of question. Metadata would be a little bit more pure data, like pure data or digital information kind of question. So let's talk about storing data. So one of the things I briefly mentioned is when we store data, if you have a data file that is huge and takes up a lot of space, you will you won't be able to store as much given the limitations of your memory that you have. So one of the topics of interest, it's always a topic of interest, is how to minimize the amount of storage that you use. And we normally call this data compression. We compress digital information. So let's see what we have on this slide. So usually simply storing data takes a lot of space. Very true statement. An uncompressed 90-minute high def movie takes up to 1 terabyte of hard drive space. So just imagine any movie that you decide to watch, or like let's say you have like just a typical movie, a 90-minute movie, and you just have it on your computer, that takes up 1 terabyte and uncompressed. So it's not processed in its purest form. It is a 90-minute movie, take 1 terabyte. I feel like most of you guys don't even have 1 terabyte of hard drive space. But if we compress this digital information, so if we apply certain algorithms to it, it doesn't take up nearly as much space. That 1 terabyte would become 65 gigabytes instead after processing it, meaning after compressing it. So what we're also going to talk about is, in this PowerPoint, is going to be compression techniques, how to make this 1 terabyte file into something that's 65 gigabytes. And if you guys remember, 1024 gigabytes is 1 terabyte. So we think about the number of times, or think about the space, the relative amount of space that you have saved. 1024 gigabytes is 1 terabyte. So that's like over 100 times the amount of space that you just saved just by compressing. So pretty impressive, or not 100, maybe I'm exaggerating. Can't math right now, but it's a lot of space that you were saving though. So that was an introduction. Now let's talk about actual image data, which is what I have promised you guys. So image data, let's talk about some vocab, starting with a pixel. So a pixel, which is shortened version for picture element. So pixel just means picture element, but shortened because as engineers, we love our abbreviations. The pixel is the basic unit of color on a computer display. So I think most of you guys are familiar with what a pixel is. So a pixel is just the smallest, like if I were to like zoom in, zoom in, zoom in into a point where I cannot zoom in anymore, we would have one small unit of color of, I guess one small unit of a screen. Lately, our pixels have become much more advanced and so nice that you don't see you can't see pixels anymore. But before, there was a time where you could see each individual pixel if you zoomed in enough. So we'll talk a little bit more about pixels in just a moment, and we will actually work with pixels firsthand in a second. Let's talk about the vocabulary words a little bit more. So the size of the pixels on the screen can change depending on the resolution of the display. So if you have a high resolution, that's great. You have smaller pixels. But if you have a lower resolution, then your image is not going to look as clean because you'll be able to see the pixels more. Larger number of pixels on display requires a smaller pixel size, which better quality image. So that would go hand in hand with the resolution. But I feel like a lot of you guys understand this. You guys have TVs, or if you guys game, you guys know like monitors and stuff. So this might not be too bad, but all you need to know for now is what a pixel is and how you're able to see, or how it directly relates to what you can see on a screen. Scanning a picture into a computer or taking a digital photo turns an image into millions of individual pixels. In order for the computer to understand them, pixels are represented as binary numbers. So once again, we come to the very, I guess we come to a very, when we dissect it all and we've decomposed it to its simplest form, we have binary numbers again. The pixels are just represented as binary numbers. Each individual pixel that we have on our screen, so this pixel, this pixel, this pixel, and those are pixels, that little block is represented as binary numbers. Large pixels can make an image, yikes, make an image look blocky, and we call that pixelation. So we will see an example of that right here. So this would look, do you guys see how blocky it is? It doesn't look like a perfect circle because our pixels are so large, and also because we don't have that many pixels to work with. We're not going to make any crazy images here. Let's tie in this image with what we just did before. So 1 pixel. A pixel is the basic unit of color on a computer display. So each one of these blocks right here is what we call a pixel. 1 pixel. The size of the pixel on the screen can change depending on the resolution of the display. Larger number of pixels on display requires a smaller pixel size. So in this case right here, our pixel sizes are large. And because our pixel sizes are large, we can see the effect of pixelation. Which is that everything just looks blocky. It doesn't, I mean, yes, we know it's supposed to represent some kind of circle, but it doesn't look as smooth as a circle itself. The circle itself looks like this. But what we see is these sharp edges that are supposed to represent a circle, but don't actually. So everything from what we talked about. Okay, so scanning a picture into a computer or taking a digital photo turns an image into millions of individual pixels. So we don't, you and I, this is introductory class, we won't be talking about pixels on a million scale. We're going to talk in the much smaller scale. So don't worry, but know that as your images become more complex. As the computing power you have is larger and the ability to understand what is going on also increases, then you could take what we've applied or what we've learned in this class and put it on a bigger scale. So it would be millions of individual pixels. And eventually you would just have a nicer looking image, a standard image that you would see every day on a computer screen. But we're not quite at that level yet. We're at an introductory level. Okay, so let's talk more about this image. We are going to focus on black and white images only for now. Black and white because we have only learned about binary, or we've learned about binary numbers. So this is what we do. And then after that, we will talk about how color can be represented. So for now, black and white images, we're going to take baby steps to a better point. We only have two colors, black and white. So binary numbers will work very well for this because binary, you only have two digits that you can use, 0 and 1. So 0 is black and 1 would be white. So for each image, you have pixels. So for, let's say this is one image. Obviously you have your pixels in here. But on top of your pixels, you have other metadata, such as height and width. So the actual data itself is the pixels, because pixels is what makes up your image. That's your data. But the data about your data, height and width, would be your metadata that comes with your image. So let's see how the metadata would affect or would affect the storing of this image. By counting the width and the height, or the number of pixels that we have 15 going up and down. That would be our height. So this is our height. And then we also have 15 going left and right. That is our width. When we see the pixels on the top row, remember 1 is white, 0 is black. So let's go ahead and see what happens here. So this is white. So this is 1, 1, 1, 1, 1, then 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1. I don't know if you guys can see that, but we are just labeling the ones that are white as 1 and the ones that are black as 0. This is how it normally works, by the way. So if you were to work with black and white images only, this is exactly how they would be stored. 1 would be white, 0 would be black. Doing the next row, we would have 1, 1, 1, 0, 0, 0, oops. I don't know why it's not letting me think it goes. 1 second. Huh. I don't know what's going on, but I could write, I just can't erase. So 0, 0, 0, 0, 0, 0, 0, 1, 1, 1. When we compare what we have for each row of pixels, that is represented by each row here. So the top row, we predicted that our first row would be 1, 1, 1, 1, 1. So 1, 1, 1, 1, 1, and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Oh, 2, 4, 5, 2, 4. Oh, I'm missing a 0. 2. Right? 0, 0, 0, 0. Oh, I'm missing a 0. There should be another 0 in there that I am missing. And then we have 1, 1, 1, 1, 1. So 1, 1, 1, 1, 1 at the very end. And then this is how your rows would go. Eventually, you would go to the very last row. So this is how your data is actually being stored technically. In fact, this is how your data would be stored. So we talked about how we derived all the rows. I mean, we didn't really derive all of the rows. We're going to pretend we derived all the rows because we know how to do one. So hopefully we should be able to replicate it for the other rows. But let's see how this translates into the actual data that we are saving right over here. So the first two bytes, remember bytes. So the 1 byte is equal to 8 bits. So the first 2 bytes, this is byte number 1, and byte number 2 is going to be our metadata. It tells us what the width and what the height is for our image. So our width is 15. Let's convert 15 into a binary number. So 15, going ahead, and I guess I'll just zoom in. That way we can hopefully save ourselves some space. So 15, to convert a decimal number into a binary number, we divide by 2. So divided, oh, Lord, why, please, don't do this to me. Sorry, I don't know why it's doing this. So 15 divided by 2, we would get 7 with a remainder of 1. 7 divided by 2, we get 3 with a remainder of 1. 3 divided by 2, we get 1 with a remainder of 1. And then 1 divided by 2, we get 0 with a remainder of 1. So when we start from the bottom and go all the way up to the top, making our binary numbers, we get 1, 1, 1, 1. But we have a byte to work with, byte meaning 8 bits, not 4 bits. So we just pad the front with leading zeros. So this 1, 1, 1, 1, 1, right here, 1, 1, 1, 1 would be this 1, 1, 1, 1, and we have extra bits. So we just pad it with leading zeros. And that's what we do for both the width and the height. So this one right here would represent the width. This one down here would represent the height. That is our metadata. Now, from after that, we can represent our rows as bytes as well, simply just by concatenating everything, and everything would be a byte. So for example, this right here is 1, 1, 1. So this is our actual data for the pixels. 1, 1, 1, 1 would be from here, 1, 1, 1, 1. Then after that, we have 1, 0, 0, 0, 0, 0, 0. Yeah, 1, 0, 0, 0. So that would be 1, 0, 0, 0. And then we have, so remember I kind of messed up on the numbers because I like lost a 0, 2, 4, 6. I lost a 0 here. So my next slide is unfortunately going to be incorrect. So I'm going to fix it right now as we go along. Actually, no, I'm just going to pretend that, so I'm not going to fix it, unfortunately, because that would alter everything that we have. But we'll just pretend that the left-hand side, that this side right here is okay, that it's the correct values for now, even though it's technically not because I messed up with the pixel, the labeling of the pixels. But we have 0, 0, 1, 1. That would be this to here, so 0, 0, 1, 1. And then I have 1, 1, 1, 1, 1, 1, 1. So this is 1, 1, 1, 1. After that, we have 1, 1, 0, 0. So this would be 1, 1, 0, 0. And after that, I have 0, 0, 0, 0. So 0, 0, 0, 0. After that, I have 0, 0, 0, 1. So 0, 0, 0, 1. And after that, I have 1, 1, 1, 1. So this is 1, 1, 1, 1. So hopefully you guys see how this is going. We just literally just like stuck them together. And this is what we're working with until we get towards the very end. So 0, 0, 1, 1. I believe we get to here. So let's say we're here. Oops. So let's say we're here, 0, 0, 1, 1. That would be I want to say it is, I don't know where this is. I don't remember where I placed this. But like it would just like keep going to the very, very end. Well, where was this from? I don't remember where this is from. But let's say that we didn't quite, let's say we had leftovers, or let's say we go to the very, very end, but we still have leftover bits. So what do you think? Actually, none of you guys are probably gonna answer, but rhetorically, what do you think would happen if we have leftover bits for our bytes? So like unused bits because we've recorded all the data from our rows, but we have leftover space when we have stored that information as bytes. So think about that while I get this set up. Part of your homework is going to be to create or recreate an image that we have provided for you. So we're going to just go ahead and toggle with the simulation from code.org that I think would be helpful for you guys to maybe get a better hold of how pixels work and thus how pixels are being stored as data. So let's say that for now we want a simple 4x4 image. So 4 as a binary number would be, oops, would be like this. 4, so this right here is binary number, oh wait, 1, 0, oh sorry, that's 8. Whoops. Let's make it smaller. Like this, 0, 1, 0, 0, 0, 1, 0, 0, that is 4. Thus we have an image width of 4 and the image height of 4. If I want to just make the height 5 for some reason, I could just do it like that, perfectly fine. So this right here is only black and white for now. We will do color sometime in the future, probably not today, now that I'm looking at the time. Let's say I just want to make an X. So an X like this and an X like this. So that means this first one right here has to be black. So I'm going to put a 0. The next two should be white. So 1, 1, and then 0, because we're trying to make an X. Then here I have white, black, white, black. So it will be white, black, white, black. Wait, sorry. Black, white, because we're trying to make an X. Or something that's supposed to be an X. And then we're going to do the same pattern on the next line. So 0, 1, 1, 0, 1, 0, 0, 1, and then 0, 1, 1, 0. So I try to make an X, but now that I'm thinking about it, it's not much of an X, but we create like an X formation here. First two lines here are our metadata. So this expresses the width and the height of our image. And then the next lines just represent every individual pixel because each pixel that we are dealing with right now is black or white. So let's say I want to do a 5x5. This completely alters everything, but now I want to make a different kind of X. So an X that is like this. X and X. So we would want 0, 1, 1, 1, 0. The spaces don't really matter. I'm putting in the spaces here. So like do you see how I have space? This changes nothing. I just put in the space there so we can make, like, it's easier to see the numbers. It's like when you write like 1,300,000 and like 76, you put the commas in there. You don't need to put in the commas there, but the commas help you differentiate each like set of 3 values because that would be each multiple of 1,000. So it's the equivalent of that. You don't need to put in the spaces. I'm just putting in the spaces for visual clarity. Then after that, this should be white and then black and then white and then black and then white. So I guess black and then white. And then after that, it should be white, white, black, white, white, white. And then after that, we black, white, black, white. And then black, white, 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 black. So this is how our data looks like. Notice the number of bytes that we have, or like the number of bits / bytes that we have right now. So right now we have this leftover 0. Does anyone, I guess once again, rhetorical question, have any idea how we could pad this data to make it work? Once again, rhetorical question. Oh, sorry. Oh no. Okay. I'm out. Okay. Well, so we could just pad it with zeros. That's the answer. And then actually someone brought something up to me and I didn't see the message until now. So actually let me go back to the PowerPoint. Oh no, now I'm sad. It looks like I made another mistake in this PowerPoint. Someone brought to my attention that the width and the height is actually 16. I counted wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is 16, this is 16. So that means all of this is incorrect. Oh no. So here, this should say, oops, this should say 1, 0, 0, 0, 0. Say 1, 0, 0, 0, 0. Because it's 16 by 16, not 15 by 15. Can't count. Okay. Sorry about that, you guys. Hopefully it wasn't a huge impediment to what we talked about, but overall, just to summarize, hopefully to clear up the confusion, we have our metadata, which represents our width and height, which is not actually like data, it's data talking about our data, because the data that is actually of importance here is going to be the pixels. So the pixels, each individual pixel is 1 bit, and we could combine them into bytes to represent what our pixels are, or what our pixels should look like. Right now, we're only using 2 colors, black and white, so it's a very simple version of what we're going to do. Hence, we have just like 1s and 0s. 0 is black, 1 is white, and then we just concatenate everything together. If necessary, you can pad the very end with zeros, and that's only used if you have an excess of bytes, or sorry, excess of bits left over, but that's not super important. For now, I'm going to skip color because I do want to talk about a different topic. We'll go back to color next week when we talk about, when we finish our discussion about data. But for now, let's talk about data compression. Actually, yeah, we'll just talk about data compression for now. So there's 2 kinds of data compression that you guys need to know about: lossy versus lossless. So when data is lost during compression, it is known as lossy compression. And hopefully, if you guys can figure out what lossless means versus lossy, I think you guys are smart. I think you guys can figure it out. Lossy versus lossless. But when you lose data, when you lose information about your data, that is known as lossy compression, because you're literally just throwing out data to save space. This is used for cases where human eye or ear cannot detect the loss of data. So for example, the human eye cannot see the difference between very similar shades of color. So when compressing an image, the computer may look at the colors that are very similar and change them all to the same color. So let's take a look at these 3 images that we have here. These are, the first one is a JPEG that is 824 kilobytes. The second one is 76 kilobytes using lossy compression. But chances are most of you guys didn't even know that they're different images. And the last one is 80% lossy compression. We have literally thrown out data so that we have 38%, or sorry, 38 kilobytes of the original 824 kilobytes. And the way that they do this is by grouping colors together that are similar. So let's say, I think the most obvious part is, I guess, like this part right here versus this part right here versus this part right here. Here you can see some kind of pixelation occurring. Do you guys see the pixelation in this instance right here? Oh, oops. Do you guys see the pixelation here? Like right here where it's becoming like more blocky as opposed to over here where there was like no blocks at all. So hopefully you guys can see that. That's because we are grouping parts of our image, and instead of storing every single information of color that we have there, we are going to generalize it so that they are similar colors. So that's the most I can zoom in. So let's say this part right here versus around here, I guess. In this instance, we could say, let's pretend each pixel has a different color. And let's say in that very, very small area, we have like 200 pixels. So that means you're storing the colors of 200 pixels in that small area. It's probably not 200, it's probably more like, let's say like, yeah, actually, let's say 200. It's like 200 pixels. So that's a lot more memory compared to, let's say, this one over here, where instead you are going to generalize the area and say these pixels are the same color. So instead of you having 200 different pixels having different colors, you could say these 200 pixels are the same color. If these pixels are the same color, then you could just save that one color and just say it applies to these, as opposed to having 200 different colors and then saying that and like storing that. So that's the idea of lossy. You want to generalize things, throw out extra information that won't take away from the image or the data itself. When we zoom out, you can't even tell. It's when we zoom in and we really look at those fine details that we could see that indeed data has been lost. But in a general fashion, it's pretty much negligible. You have literally lost 80% of your data here, but you can't tell. So this is an advantage of lossy compression. However, you can see that the resolution and the quality has reduced in some ways. When you compress data without losing any details, this is called lossless compression. So this is useful when you have to maintain all original information it had before it was compressed. So let's say you're doing meticulous research and you require an exact solution. So that data that you have, you don't want to compress your data. You want to have the exact precise data that you had before. but you still have to compress it somehow. So you can't use loss compression, otherwise you will lose parts of your data. So what we do instead is lossless compression, where it will be compressed in a way so that when you decompress it, you will have the exact same file, same data as you had before. We normally use lossless data compression when we have files, so text files in particular. This requires more work than just throwing out the data because it requires some kind of pattern recognition. And let's talk about that right here. So an example of lossless compression is text compression. So when it comes to text compression, you, instead of removing things from the document, because if you took out like this word, this word, this word, this word, how woodchuck chuck if a woodchuck could chuck wood would not be the same as what we had before. How much wood could a woodchuck chuck if a woodchuck could chuck wood? So what we try to do instead is find patterns in the data. So let's erase this. When we take a close look at what we have here, how much wood could a woodchuck chuck if a woodchuck could chuck wood? We could see overlaps in the words. Wood, could, woodchuck, chuck. Like wood, we have wood, and then could, and then chuck. So those are the reoccurring words here. So rather, remember each word or each character. So remember, each character is one byte. And remember, 1 byte is 8 bits. So here, would, this here, this is 4 bytes. Could is 5 bytes. Would is again, whoops. Would is again 4 bytes. Chuck is 5 bytes, and then so on and so forth. So the strategy here is there's a lot of similarity, but instead of using these words that are like 4 to 5 bytes each, we could use some kind of code or not really encryption, but some kind of symbol to represent these. Right now I'm just using a tree, but ideally you would use another character, which is 1 byte. So 1 byte versus 4 bytes. So we have 1, 2, 3, 4 bytes, 4 of these, so we have 4 bytes versus the 4 times 16 bytes that we had, or sorry, 4 times 4, which is equal to 16 bytes that we had before. Because each would, W-O-O-D, is 4 bytes. We have 4 different substitutions that took place. So 4 times 4 is 16. So we've thrown out 16 bytes and instead substituted it with 4 bytes in total, 1 byte for each substitution that we had. After that, we could probably also do it the same thing for chuck. So this is the same thing as how much wood could a wood chuck if a woodchuck could chuck wood. Same thing going on here. This is 5 characters, so this is 5 bytes. This 1 character is 1 byte. So we have made 4 substitutions again. So this is 4 bytes compared to the 4 times 5 bytes that we had before. So we've substituted 20 bytes and in place used 4 bytes. And then we also could do it the same thing for could. We could replace a star. So now it says how much wood could a woodchuck chuck if a woodchuck could chuck wood. Same thing. So we went from having 58 total characters to 22 total characters. So this doesn't seem like a lot. Simple compression, however, did make the file 30% smaller. So imagine if you did it on a very large scale file where there's for sure going to be words that are repeated, like and, or like different articles that you always use in everyday language. It'll add up. So this is an example of lossless compression, where you are trying to find patterns in the data that you have, making substitutions, and then when you decompress the file, it will come back to its original form. Because really, as we were going through this, I knew exactly what was what, because I know that this is wood. So every single time I see this, I would say wood. If this right here is could, every single time I see a star, I say could. And then we have chuck, which for the basketball. So every single time I see that, I know it's chuck. So we could, if we can translate it one way, we should be able to retranslate it back into the original, which is what's so special about lossless compression as opposed to lossy. Lossy, you're literally throwing out data that's not important. That's key. If it's not important, it's okay to throw it out, and it won't affect the actual interpretation of the data. Whereas for lossless compression, you don't want to lose data. So instead, you want to find patterns to compress the data and reduce the amount of data that is being stored, but in a way so that you could translate it back into the original state that it was in before. So to be honest, there's actually something that we could do even more to this. Hopefully you guys can see that wood and chuck, those two could be combined together for woodchuck, and then we could replace it with this as well. So now it's how much wood could a woodchuck chuck if a woodchuck could chuck wood. So we could reduce it even more using like a compression on top of a compression, or a substitution on top of a substitution rather. So now it comes down to these three options: 58 bytes versus 22 bytes versus 20 bytes. And hopefully you guys will opt for the 20 bytes more, just because it is a, it's smaller. And the smaller your data is, you're not losing anything, you're not losing the actual data itself, but the smaller the data is, the better for you when you're storing data. So once again, here is another example of lossy. Oh, it's not updating. Ah, there we go, lossy versus lossless. You can see that hopefully this one right here is not as, or like when we look at the bird itself, and we also look at the branches, it's not as clear as its counterpart on the left. So this right here is a lossy compression from the original, because we are generalizing certain parts of our picture and making the quality lower, unfortunately, because we're throwing out parts of the data. However, on a general scale, it doesn't take away much from your picture. You're still able to understand that these two pictures are identical. So pick and choose your battles. Which one would be better for you? Would it be lossy or would it be lossless? So today we talked about actually quite a lot. We talked about an introduction, or compressing, or not compressing. First of all, we talked about images, how images are stored in the form of pixels. We talked about metadata. I also introduced the concept of big data. And finally, we talked about text, or just general data compression in the form of images and also text compression. Next week, we're going to finish up our data section by talking more about images, specifically how colored pixels are stored. We'll also mess around with that quite a bit next week as well. And we'll also should have time to start our next unit, which is talking about the internet, how the internet was formed, how certain things are being done on the internet, such as data transfer, or how packages are delivered. So keep an eye out for that